Have you ever wondered why even the best experiments can sometimes go wrong? Why do we often find discrepancies in our results despite our best efforts? Welcome to my channel. In today's video, we will dive deep into the world of errors in measurements and experiments. We will explore the different types of errors that can throw your data off course, and more importantly, I will arm you with practical strategies to minimize these errors and boost the accuracy of your results. So let's get started. In my last video, I already discussed what error means and how we can calculate the value of errors in any experiment. So in this video, I will discuss the types of errors and how to minimize them to get accurate results. Errors are generally of two types: determinate and indeterminate. Determinate errors are also named as systematic errors, and indeterminate errors are named as random errors. Let's start with determinate or systematic errors. The term systematic in this context refers to the systematic nature of these errors. They occur systematically or regularly under certain conditions. These errors are consistent and repeatable, caused by flaws in the measurement system itself. Think of them as built-in biases, like a scale that always reads 5 grams too heavy or a clock that's always 2 minutes fast. Key characteristics of determinate errors include consistency. Determinate errors occur consistently under specific conditions, impacting measurements or experimental results in a predictable manner. Next one is predictability. The effect of determinate errors can be anticipated and accounted for once identified, allowing for correction or adjustment in subsequent analysis. Next characteristic includes sources. Determinate errors often stem from systematic flaws in the measurement instruments, calibration procedures, experimental setups, or environmental conditions. And last one is cumulative impact. Because determinate errors consistently influence results in the same direction, they can accumulate over repeated measurements or experiments, potentially leading to significant inaccuracies if left unaddressed. Overall, determinate errors are systematic in nature, meaning they arise from identifiable sources and produce consistent biases that can be corrected through appropriate calibration, adjustment, or control measures. Understanding and mitigating determinate errors are essential for ensuring the accuracy and reliability of scientific measurements and experimental findings. Determinate errors, also known as systematic errors, arise from identifiable and usually correctable causes. These results in measurements that are consistently biased in a particular direction. Some common sources of determinate errors include instrumental errors, observational errors, procedural errors, reagent related errors, theoretical errors, and operational errors. Identifying and correcting these sources of determinate errors is crucial for improving the accuracy and reliability of measurements in scientific and technical work. So let's learn about the types of determinate errors. Determinate errors are divided into 5 usual types. These are analyst related errors, operational or personal errors, transcription errors, reagent and instrument related errors, and analytical method related errors. So let's start with analyst error. Analyst error, often referred to as human or operator error, It is a type of error introduced by person conducting the experiment, measurement or analysis. These errors can stem from various sources and can significantly impact the accuracy and precision of the results. Analyst errors can stem from various sources, including misreading instruments, recording mistakes, procedural deviations, calculation errors, sampling issues, interpretation mistakes, and documentation errors. Misreading instruments refers to the act of incorrectly interpreting the readings or measurements displayed by various tools or devices used in experiments or analysis. Recording mistakes results from human error due to mishearing information, distractions during data entry, or any other analysis related cause. Procedural deviations refers to instances where individuals conducting experiments or analysis deviate from established protocols or procedures. It may happen due to a lack of adherence to standard protocols, a misreading of procedures, or the belief that alternative methods may yield better results. Calculation errors refer to inaccuracies or mistakes made during the process of performing mathematical calculations. Sampling issues can arise due to various factors, including inadequate sample size, non representative sampling methods, biased sample selection, contamination of samples, or sampling from inappropriate locations. Interpretation mistakes occur when individuals misinterpret or misjudge data, observations, or results during the analysis or evaluation process. These mistakes can result from various factors, including an incomplete understanding of the data, misapplication of statistical methods, or overlooking alternative explanations. Documentation errors refers to inaccuracies, omissions, or inconsistencies in recording and maintaining records or experimental procedures, observations, and data. Documentation errors can occur due to factors such as human error, incomplete or illegal records, failure to update documentation promptly, or miscommunication among team members. Next is operational error. An operational error refers to a mistake that occurs during the execution of a task or operation. This type of error typically results from human actions, such as by individual analysts, rather than system malfunction or procedural flaws. Operational errors can include miscommunication, incorrect data entry, failure to follow established procedures, or other mistakes made by individuals during the performance of their duties. These errors can affect the efficiency, safety, and outcomes of operations in various fields such as manufacturing and healthcare. Examples include mechanical loss of materials in various steps of analysis. This may occur due to analyst ignorance. It generally refers to unintentional wastage or reduction of materials during various steps of an analysis caused by analysts' lack of knowledge, attention, or adherence to proper procedures. Second example is underwashing or overwashing of the precipitate by the analyst during any analytical procedure. It refers to the errors made during the washing step of a precipitate in an analytical procedure. These errors occur due to the analyst's failure to follow optimal washing protocols. An operational error may also occur due to an analyst's inability to judge color changes in visual titration. It refers to mistakes made during a titration process because the analyst cannot accurately perceive or interpret the color change that indicates the endpoint. The carelessness of an analyst during analytical procedures results in incorrect measurements, mislabeling or misidentification, contamination of the sample, and several procedural errors. Third type of systematic errors include transcription errors. Transcription errors are mistakes that occur when spoken words are converted into the written text. These errors can occur for a variety of reasons and can significantly impact the accuracy and readability of the transcribed text. Some common types of transcription errors are errors that are made through omissions, such as skipping words, phrases, or entire sentences. Insertion errors occur due to the addition of extra words or phrases that were not present in the original speech. Substitution errors occur when replacing a word with another that sounds similar but has a different meaning, such as use of homophones. Incorrect spelling of words causes misspelling. Sometimes, incorrectly transcribing words or phrases results from misunderstanding the context or meaning and causing misinterpretations. Punctuation errors are caused by the incorrect use of punctuation marks, which can change the meaning of sentences. Capitalization errors are common in transcription errors and occur due to the improper use of uppercase and lowercase letters. And lastly, speaker identification errors occur due to misattributing statements to the wrong speaker in multi speaker transcriptions. The most common reasons for transcription errors are poor audio quality, fast or unclear speech, human fatigue, or limitations in transcription software. Next type of systematic errors are due to reagents and instruments. Reagents and instrument errors are critical issues in various scientific and industrial processes, especially in laboratories. These errors can affect the accuracy, reliability, and validity of experimental results. Understanding these errors and how to mitigate them is essential for ensuring high quality outcomes. Errors made due to the presence of impurities or contaminations affect the reaction process and measurement. These errors becomes more prominent in the determination of analytes with lower concentrations. Contamination in reagents can cause unwanted side reactions or interfere with the primary reaction, leading to errors in results. For example, using impure solvents in chromatography can affect peak resolution and retention times. Let's understand errors due to reagents. Degradation or decomposition of reagents over time, especially if not stored properly, is a common cause of determinate errors. Degraded or decomposed reagents might not react as expected, causing systematic deviations in results. Sometimes prepared reagents may also be improperly labeled. This can lead to the use of incorrect amounts in reactions, affecting the stoichiometry and outcome of the experiment. Sometimes errors are caused by not considering the stability issues with the chemicals. Some reagents may be sensitive to environmental conditions such as light, temperature, or humidity. For example, light sensitive reagents can degrade if exposed to light, leading to inconsistent results. Determinate errors are also related to the instrument used in experiments. Incorrect calibration of these instruments can cause calibration errors. So, the instruments that are not properly calibrated will produce biased measurements. For example, a balance that is not zeroed correctly will consistently give incorrect mass readings no matter how many times you repeat the procedure. Sometimes instruments drift out of calibration over time due to wear and tear, leading to systematic errors. Errors due to the faulty construction of balances can significantly impact the accuracy and reliability of mass measurements in scientific experiments. These errors are often systematic and can lead to consistent deviations from the true value. Some common issues with balances are uneven pans, defective pan supports, worn out bearings or knife edges, misaligned components, frame instability, etc. All these can contribute to errors related to the faulty construction of balances. Sometimes incorrect instrument alignment can cause various types of systematic errors, impacting the accuracy and reliability of measurements. For example, if a balance is not at the proper level, the distribution of mass can be uneven, leading to inaccurate measurements. Also, misalignment of optical components such as mirrors, lenses, grating, etc., can lead to incorrect wavelength readings and poor spectral resolution. Lastly, an incorrect wavelength setting is a common source of systematic errors in experiments involving spectroscopic instruments such as ultraviolet visible spectrophotometers, fluorescence spectrophotometers, and other optical instruments. This can affect the determination of concentration, reaction kinetics, and other analysis dependent on precise wavelength measurements. Next are analytical method related errors. These errors can significantly impact the accuracy, precision, and reliability of experimental results. These errors can arise from various sources, including sample preparation, instrument calibration, method selection, and data analysis. For example, incorrect sampling, such as failure to obtain a representative sample, can lead to biased results that do not accurately reflect the true composition of the sample population. Another reason for analytical method related errors arises from incomplete reactions. These reactions significantly affect the accuracy and reliability of the analytical methods, such as if any reaction does not proceed to completion, the expected product yield is lower and unreacted reactants may remain. Most of the time, these unreacted reactants lead to erroneous conclusions in quantitative and qualitative analysis. Sometimes, loss of analyte during sample preparation due to volatilization or precipitation can introduce several errors in analytical methods. For example, if the analyte volatilizes during sample preparation, the concentration of the analyte in the final solution will be lower than the actual concentration in the original sample. This can lead to an underestimation of the analyte concentration in the analysis. In the titrometric analysis, if the titration reaction fails to proceed to completion, the endpoint of the titration may be inaccurately determined. This can lead to errors in the calculated concentration of the analyte. Incomplete reactions can occur due to factors such as insufficient mixing, inadequate reaction time, or improper stoichiometry. Last but not the least, in gravimetric analysis, decomposition, co-precipitation, or post-precipitation are the main reasons for erroneous results. For example, if the precipitate formed during gravimetric analysis is not stable under the conditions of drying or ignition, it may decompose, leading to loss of the analyte. This can result in underestimated values of the analyte concentration. Co-precipitation occurs when impurities or other substances present in the solution are inadvertently incorporated in the precipitate along with the analyte. This can lead to an overestimation of the analyte concentration, as the measured mass of the precipitate include both the analyte and the impurities. Also, sometimes the adsorption of contaminants on the precipitate surface or the formation of hydrates or other chemical species can alter the mass of the precipitate and affect the accuracy of the analysis. This is known as post precipitation. So now, as we know about the types of determinate errors, let's learn how we can minimize or eliminate them by using suitable methods. Modern analytical science uses various important and advanced methods to minimize errors. These methods include calibration of apparatus and instruments, control determination, blank determination, an independent method of analysis, parallel determination, internal standards, amplification method, and isotopic dilution method. Let's start with calibration of apparatus and instruments. Calibration ensures that the instruments and apparatus used in the analysis are operating accurately and reliably. Regular calibration of standard reference materials establishes the relationship between instrument response and analyte concentration. Proper calibration reduces systematic errors associated with instrument drift or inaccuracies, improving the accuracy of measurements. Next is control determination. Control determination involves analyzing samples with known concentration of the analyte to monitor the performance of the analytical method. By comparing the measured values to the known concentrations, any systematic errors or biases in the analysis can be identified and corrected. Control determination helps in ensuring the accuracy and precision of the analytical results over time. Next method is blank determination. Blank determination involves analyzing samples that do not contain the analyte of interest. Blank determination helps in the identification and correction of sources of contamination or background interferences that may affect the accuracy of the measurements. Subtracting the blank value from the measured sample value eliminates the contribution of background signals, improving the accuracy of the results. Next method is independent method of analysis. Utilizing an independent method of analysis involves employing a different analytical technique to determine the concentration of the analyte. The comparison of results obtained from different methods provides validation and confidence in the accuracy of the measurements. Discrepancies between results from independent methods can indicate potential errors or limitations in one of the methods, prompting further investigation or refinement of the analytical procedures. Next is parallel determination. Parallel determination method involves performing multiple replicate analysis of the same sample under identical conditions. Replicate measurements allow for the assessment of the precision and repeatability of the analytical method. Consistent result obtained from parallel determinations provide confidence in the reliability of the measurements and help in the detection of any outliers or anomalies. Internal standards are compounds of known concentration that are added to samples prior to analysis. Internal standards serve as a reference for quantification by correcting the variations in sample preparation, instrument response, and matrix effects. By measuring the ratio of the analyte signal to the internal standard signal, variations in the instrument performance and sample composition can be compensated for improving the accuracy of the results. Next method is amplification method. Amplification method involve enhancing the signal of the analyte to improve detection sensitivity and accuracy. Techniques such as preconcentration, derivatization, or signal enhancement through chemical reaction can amplify the signal of the analyte. Amplification method enable the accurate quantification of low concentrations of analytes that may be near the detection limit of the analytical method. Next is isotopic dilution. Isotopic dilution involves addition of a known amount of isotopically labeled analyte to the sample. The isotopically labeled analyte serves as an internal standard for quantification, allowing the accurate determination of the analyte concentration. Isotopic dilution corrects for losses during sample preparation and matrix effects, improving the accuracy of the measurements. By implementing these strategies, errors in the analytical methods can be minimized, leading to more accurate and reliable results in the chemical analysis. Now let's learn about indeterminate errors. Indeterminate errors, also known as random errors, are a type of error that occur in scientific measurements. These type of errors cannot be pinpointed to any specific well-defined reasons. These errors do not have a clear identifiable cause. Unlike systematic errors which can be traced to a specific source, indeterminate errors arise from a variety of unpredictable factors. They might include slight variations in the experimental conditions, the inherent limitations of measurement instruments, or minor fluctuations in the environment that are too small to control or detect. Indeterminate errors are random in nature. These are characterized by their randomness. This means they do not follow a predictable pattern and can vary in magnitude and direction each time a measurement is taken. For example, if you repeatedly measure the same quantity under seemingly identical conditions, the results will differ slightly each time due to these random errors. Indeterminate errors take place in several successive measurements performed by the same analyst under the same conditions and identical experimental parameters. Even when the same person performs a series of measurements using the same procedure, tools, and conditions, indeterminate errors can still occur. This reinforces their random nature and highlights that even controlled environments cannot completely eliminate these errors. In a sense, indeterminate errors are an unavoidable aspect of scientific measurement due to their inherent unpredictability and the minor uncontrollable variations in the measurement process. Indeterminate errors are caused by various sources which are characterized in three main categories, including instrumental factors, human factors, and chemical and physical factors. Instrumental factors include instrumental noise, which refers to random fluctuations and disturbances that can affect the accuracy and precision of measurements taken by scientific instruments such as spectrophotometers. Environmental variations include external conditions such as temperature, humidity, air pressure, and electromagnetic interference. These variations can affect the performance of instruments and the stability of samples. For example, temperature changes can alter the sensitivity of electronic components or the reaction rates in a chemical analysis. Sample handling includes all processes involved in collecting, transporting, storing, and preparing samples for analysis. Poor sample handling can introduce contamination, degradation, or changes in the sample composition. In human factors, measurement precision refers to the consistency and repeatability of measurements when performed under the same conditions. Human factors that can affect precision include the skill and experience of the operator, the clarity of procedural instructions, and the level of attention to detail. Sample preparation involves the steps taken to make a sample suitable for analysis, such as dilution, filtration, or chemical treatment. Human factors in sample preparation include the accuracy in measuring reagents, the thoroughness of mixing, and the timing of preparation steps. Inconsistent or incorrect sample preparation can lead to variability and inaccuracies in the results. In chemical and physical factors, chemical interferences occur when the substance in the sample interact with analyte or the detection method, leading to erroneous results. The physical properties of the sample, such as viscosity, particle size, and phase, can significantly influence analytical measurements. For instance, highly viscous samples may be difficult to handle and measure accurately, while heterogeneous samples can lead to uneven distribution of analytes. Minimization of indeterminate errors. Ensuring following important things can help in minimizing the indeterminate errors. Increase the number of measurements. Performing more measurements and calculating the average of the results reduces the impact of random errors. Improve instrument precision. Using more precise and high quality instruments ensures reduced measurement variability. Maintain consistent conditions. Ensuring stable environmental conditions such as temperature, humidity, etc., reduces environmental effects. Use of standardized procedures. Following consistent and well documented standard procedures minimizes the variability of the results. Training and practice. Ensuring that the analyst is well trained and experienced reduces operator related variability. Use statistical methods. Statistical methods can identify and reduce the random errors in the data. While it is impossible to completely eliminate indeterminate errors, these steps can help reduce their magnitude and impact on results. Thank you for watching this video. For more updates, kindly subscribe to my YouTube channel, Pharm Tech Insights.